Section 5.8 covers inverse trig functions. And there's going to be three of these that we're going to look at. And if you look at the theorem here, it shows the three that we're going to focus on. So the first one, notice they all have something in common there. They all have an a squared, they all have a u squared. All right, it's just a matter of recognizing which form you're seeing. Okay, so the first one is for arcsine, the next one is arctan, and the last one is arcsecant. All right, so let's work through some of these. Once you work through a few, you can get the hang of it. So I'm going to always try to rewrite something so we can easily recognize what we've got. So for this first one, I want to rewrite this as the integral of 1 over root 1 squared minus 2x squared dx. All right. So if you look up at the top, the thing that looks most closely like that is the very first one, right? You see this root a squared minus u squared. All right, so I'm going to let u be 2x, then du will be 2dx. So I don't see a 2 anywhere, so I'm gonna have to multiply by 1/2. All right, so that takes care of my u, and then a will be 1. All right. So now I'm going to rewrite the whole thing as 1/2 times 1 over root a squared minus u squared du. Okay, so everything there is defined. I defined a as being 1. I defined u as being 2x. So everything there is accounted for. All right, so now we're just going to apply the formula for 1 over root a squared minus u squared du. And that's going to be arcsine of u over a plus c. And then the last step is just to fill in the values. So arcsine, u we said was 2x, and a is 1. So this is just 2x. Arcsine of 2x plus c. So the key here is just make sure you define u and a, and make sure once you have u, of course, you have to, it's like a u substitution. So you have to take the derivative of that, and then if you have any extra multipliers, like in this case we have the 1/2, make sure you deal with that. But otherwise, we're just going to use the formula once we identify the pattern. All right, let's take a look at this one. Now this one is very similar to the third one. All right, because you see we have the x out in front. We've got the x there, and the only one that has the x in front of the root is number 3. All right. Okay, so let's start by rewriting this. First of all, I'm just going to bring that 5 out to the front, because this is a constant multiple. All right, so I got 1 over x times the square root. I'm going to make that 3x squared minus 11 doesn't have any, easy root. So we're just going to write it as root 11 squared. All right, just so it fits the pattern, dx. All right, so we're going to let u be 3x. Then du is 3 dx. Okay, so there's no 3, so we've got to do the 1/3 on both sides. All right, so we'll just multiply that times the 5. So we're going to end up with 5/3 times the integral of 1 over the square root of u squared minus a squared. So our a is going to be root 11. Okay. Now the thing we have to deal with next is that x. All right. We've got an x there. We can't just write an x out there because it's got to be in terms of u. Let me go back to the formula real quick. Yeah, if you look at that formula, you've got u out in the front. Okay. Well, we said that u was 3x. Okay. So the way you deal with this, it's kind of like those ones in the previous, I think it was the section where we first did the u substitution. What we're going to have to do here, remember we said that u is equal to 3x. That means x is equal to u over 3. Okay, so we can write u over 3 here. Well, by doing that, we can pull that 3 out to the front. Okay, so I'm just going to do a preliminary step here. Let's put the 3 on the top first, and then the u on the bottom. All right, so now the bottom looks like the formula. All right, bottom looks like the formula. Right, we have u, and then we have the root of u squared minus a squared. So it looks exactly like that. And then with that 3 on the top, we can just take that out in the front. Well, we already have something over 3, so why don't we just cancel it out? Cancel this 3 out, make it a 1. Cancel that 3 out, make it a 1. Right? So now we just have 5 times the integral of 1 over u times u squared minus a squared du. All right. All right, so that's going to be 5 times, and I'm just going to write the formula. It was 1 over a arcsecant of absolute value of u over a plus c. Okay. So now I just fill in what I know for a and u. So this is going to be 5 times, let's put the root 11 on top. Root 11's on the bottom. So 1 over root 11 arcsecant. U we said was 3x. So absolute value of 3x over root 11. And then plus c. And you can distribute the 5, so you could write it as 5 over root 11 arcsecant. of absolute value of 3x over root 11 plus c. Now note the 5, we wouldn't multiply the 5 times the c, but remember c is just a constant, and that constant could be anything, so 5 times the constant is just another constant. Right? Okay, so a lot of times these are just going to be pattern recognition. All right, so look at this next one. Now this one is a little bit different. It's got x squared plus 8 in the numerator. So we have to deal with that. Okay. Now, in the previous section, we had some problems where I said if you had the power of x in the numerator greater than the power of x in the denominator, you want to divide it out. All right, so that's what we're going to do here. So I'm going to take the integral and just split it up. So you've got x squared over x times root x squared minus 4 dx, and then plus the integral of 8 over x times root x squared minus 4 dx. Okay. So for that first integral, I got x squared over x. So let's just make that x over root x squared minus 4 dx. And plus, I'm just going to go ahead and pull that 8 out right now. Deal with that. Over x times root x squared minus 2 squared. All right. So that second integral there, it looks just like the one we just did, right? Where we had the u on the bottom and the root of u squared minus a squared. Okay. The other one, the root x over root x squared minus 4, that one you can do a u substitution for, right? Okay, so I'm going to do the first integral. I'm going to let u be x squared minus 4, and du is 2x dx. All right, so I got that x on the top. So to make it an x, multiply both sides by 1/2. All right. So that first integral turns into 1/2 of 1 over root u du. Okay. Which when we rewrite that, it'll be a relatively easy integral to solve. All right, now let's look at the second integral. Second integral is exactly the pattern we see for the arcsecant. Okay, let's go back to the arcsecant formula. All right, so in place of the u, we got x, and in place of the a, we got 2. Okay. So I'm going to go ahead and define everything. Let's change to a different color. Go to green. So second integral. We're going to let u is just going to be x, right? and then du is dx. All right, so no problem there. We don't have to make any changes or anything. And a is going to be 2. All right, so we got plus 8 times the integral of 1 over u times root u squared minus a squared du. So it looks exactly like what we have in our formula. Okay, that first integral, I'm going to go one more step on it. So we got 1/2 integral. We can write this as u to the negative 1/2 du. Okay, and then plus 8 times the integral of 1 over u times root u squared minus a squared du. Okay, so the first one, that's going to be 1/2. Let's see, u to the 1/2 plus 1 is 1/2 over 1/2. And the 1/2 and 1/2 will cancel. So that's just u to the 1/2. And then the second integral, we've got plus 8. And this is the arcsecant. So this is going to be 1 over a arcsecant, absolute value of u over a plus c. Okay. Now that first one, we're just going to, well, both of them, we're going to just back substitute the values in. Okay, so remember we canceled out the 1/2 and the 1/2. So this is just going to be x squared minus 4 to the 1/2. Or you could write it as the root, either way. And then that second integral, let's see, we have 1 over a, so that's just going to be 8 over 2, right, or 4, secant of absolute value of x over a, which is 2, and then plus c. Right. So I may have lost you where I got that 4. The 1 over a is 1 over 2. 8 times 1 over 2 is 4. So that's how I got that. All right, take a look at this next one. This one's pretty straightforward. If you want, you can rewrite it. I always like to write it so I see the pattern, right? So I got 2 squared minus x squared. And if you look up here, look at the formulas. Root 2 squared minus x squared, that's the first one, right? That's the arcsine one. Okay, now this one's a definite integral. So this is going to be arcsine. Oh wait, hang on a second. I didn't define everything. Let me, I'll do it again using the U notation. So we're staying consistent. All right, so U is equal to X and du is dx. And then A is equal to 2. All right. So we've got the integral of 1 over a squared minus u squared du. All right. Now, since u is equal to x, our limits aren't going to change at all, right? So this is still 0 to 2. So then we have arcsine, arc. I think I misspelled that. Let's try that again. Arcsine of u over a from 0 to root 2. And now I'm just going to fill in what the u and the a are. So that'll be arcsine root 2 over 2 minus arcsine 0 over 2. Arcsine of root 2 over 2 is pi over 4. And arcsine of 0 is 0. So this is just pi over 4. All right, let's take a look at this next one. Now this one I'm going to rewrite so we can recognize the pattern we have here. I'm going to go ahead and write this as 1 squared minus e to the negative x. Squared dx. All right, so if you take e to the negative x and square it, that's the same as taking the 2 and multiplying by the negative x. So we get e to the negative 2x. All right, so this is actually a square over here. All right. But now that makes it one of the patterns that we're seeing for one of the inverse tangent functions. All right, so let u be e to the negative x. Then the derivative of that is negative e to the negative x dx. Okay, so we see that e to the negative x on the top, and we don't have the negative, so move the negative to the other side. All right, so now we'll be able to write it in recognizable form here. I should have given myself more room, but oh, we're going to change our limits here on this one. All right, so I've got 1 over, oh, I didn't define, let's say a is equal to 1. So a squared minus u squared. And that's a root du. All right, so like I said, I'm going to change my limits. So my upper limit will be e to the negative ln4. All right, now e to the negative ln4 is the same as e. Remember, if you have a log, you can take uh, the multiple at the front and move it up as the exponent. So this will be e to the natural log of 4 to the negative 1. And remember, if you have e to the ln, it just cancels out. So we end up with 4 to the negative 1. 4 to the negative 1 is 1 over 4. Okay, so our upper limit's going to be 1/4. And then our lower limit, that'll be e to the negative ln2, which is 1/2. Okay, so now we've changed our limits. We did our u substitution. And now we'll just use the pattern, which is going to be arcsine, right? So this is going to be, oh, I forgot my negative out front there. I've got negative arcsine of u over a from 1/2 to 1/4, which is negative arcsine. U is, well, u is u and a is 1, right? So it's u over 1 from 1/2 to 1/4. So this is going to be negative arcsine of 1/4 minus arcsine of 1/2. Okay. And let's see, arcsine of 1/4. I don't think that's anything. So it's just negative arcsine of 1/4. Arcsine of 1/2. Let's see, what is sine of pi over 6? I believe it is. Yeah. So minus pi over 6. And let's see. Oh, that'd be plus. That'd be a plus, right? Because we got negative outside the bracket and distributing inside the bracket. That would become positive. Give yourself a 1/4 point for that. All right, let's look at this next one. This one looks a little tricky as well. But we know that if you let u equals sine x, then du is cosine x dx. Okay, so we could rewrite this as the integral of 1 over 1 squared plus u squared du. Okay, so this is the one that is for arctangent. Let's go back up and look at the formula. The middle one, you got a squared plus u squared. Okay, so here we have a squared plus u squared. So a is equal to 1. All right. And then I'm going to go ahead and change my limits. All right. So upper limit will be sine of pi over 2. Sine of pi over 2, I believe, is 1. And our lower limit, that'll be the sine of 0, which is 0. So 0 to 1. Okay. All right, so let's see. This is going to be 1 over a arctangent of u over a from 0 to 1. Okay, so 1 over a, that's just 1. So this is just going to be arctan of u, which is going to be the 1. Arctan of 1 minus arctan of 0. Arctan of 1 is, let's see, that's going to be pi over 4. Because the tangent of pi over 4 is 1. And the arctan of 0 has to be 0. So it's just going to be 1/4. This next section involves completing the square. Sometimes the pattern isn't obvious, right? You look at this, you don't see any a squared plus u squared, a squared minus u squared, anything like that, right? But if we complete the square, we're going to see that pattern. Okay, so let's see if you recall how to complete the square. So we're going to take the denominator, x squared plus 4x plus 8, and we're going to try to write an equivalent with the squares in it. All right, so remember, you want to have the first two terms inside the parentheses and leave some space where we can complete the square. And then we have the plus 8 on the outside. Okay, so remember, to complete the square, you take the b term over 2 and square it. Okay, so that comes down here as your, and that's always going to be positive. So if you take the b term, which is 4, divide by 2, that'll be 2, square it, that's also 4. Okay, now that'll give us a complete square. But what we did, we added plus 4 on the right-hand side of the equation. You can't just write plus 4 on the right-hand side of the equation and it's still equal to x squared plus 4x plus 8. So we have to subtract 4 outside those parentheses. Right. So if you add all that together, we're still going to get x squared plus 4x plus 8, because the 4 and the minus 4 would cancel. But this enables us to write this as x plus 2 squared, and then 8 minus 4 is plus 4. Okay. So now we have we've got x plus, I forgot to put the square on there. Let me, I'm going to do this in reverse because our pattern's going to be a squared plus u squared on this one. All right, so I just want to, and I can write these in whatever order I want to because they're added, right? So let's do it as 2 squared plus x plus 2 squared dx. All right, then I can let u be x plus 2, and du equals dx. And then my a term is going to be 2. All right, so here's my u, here's my a. All right, so now I have something that's recognizable. So let's draw it like that. So 1 over a squared plus u squared du. Okay, so now all I need left, all that's left here is my limits. So my upper limit is 3 plus 2. Remember, we're using this. And this, that's 5. And then my lower limit, I'm going to use that -2. That'll give me 0. So this is just going to be 0 and 5. All right, the pattern for a squared plus u squared on the bottom is arctan. Okay, and it's 1 over a arctan u over a from 0 to 5. So that's 1/2 arctan of u over 2 from 0 to 5. Now we don't want to go back to what our u was because we changed our limits. So this is going to be 1/2 arctan of 5 over 2 minus 1/2 arctan of 0 over 2. So it's just 1/2 arctan 5 over 2. Because arctan of 0 over 2 is arctan of 0, which is 0. Okay, so these a little bit tricky, but you might see this on your WebAssign problems. This one, I've got a hint here. So on the top we've got 2x minus 5. On the bottom you've got x squared plus 2x plus 2. Now if we just had like minus 5 on the top, we could easily use that process we just went through. But this one has 2x minus 5. So the best thing to do here is to split it into two integrals. Okay, so it gives you a hint there. Let's make 2x minus 5 the same as 2x plus 2 minus 7. All right, because this is equal to that. So the first integral will be 2x plus 2 over x squared plus 2x plus 2. And there's a reason why we're doing that. You'll see here in a minute. And then we have minus 5. I'm sorry, minus 7. And I'm just going to go ahead and bring that 7 out to the front. And then I've got x squared plus 2x plus 2 dx. Okay. So the reason that hint was given, if you look at that first integral, you'll notice that the top is the derivative of the bottom. Okay, so let's deal with this in two different integrals. Okay, so the first integral, let u be the bottom. And then the derivative of that du is 2x plus 2 dx, which is the top. Okay. All right, so we can write this as the integral of 1 over u du. Okay, so that's an easy integral. That's just the natural log of u. And then for the second integral, let me change to green here. That's where we're going to use the completing the square. Okay, second integral, we're going to complete the square. So x squared plus 2x plus 2. Isolate the first two terms. Put that in parentheses. And the plus 2 on the outside. Remember, to complete the square, you take the b term, divide by 2, and square it. The b term is 2. 2 divided by 2 is 1. Square it. So this is a plus 1. And then, since we added 1, we got to subtract 1 as well. Okay. So now we can write the first in parentheses as a perfect square, and then plus 1. All right. So we can write that as, if we let u be x plus 1, du would be dx, so no problem there. And a would be 1. Okay, so we can write this as 1 over u squared plus a squared du. All right, so now we got two fairly easy integrals to evaluate. Like I said, the first one is just going to be the natural log of u. The second one is going to be 7 times arctan of u, and then plus c. Because a was 1. Remember, a was 1, so you don't have to worry about writing 1 over 1 at the front of arctan. All right, then just fill in your u's. Okay, now notice we got u's defined as two different things. One's in red, one's in green. A lot of times, if you've got situations like this, you could let, like the first integral, you can use u. You can do the u substitution. For the second integral, you could use w. Okay, I should have color-coded this since I didn't do that. So here we'd have like arctan of w, and we would have defined w as being x plus 1. All right. But since I just color-coded them and did them separately, you could also say one is u sub 1, like u sub 1 and u sub 2. You could have done it like that as well. Whatever you can do to keep track of the two different u's. Okay. So my u in the first integral was the x squared plus 2x plus 2. And then the second integral, minus 7 arctan of, we said it was x plus 1. And then plus c. All right, so that would have been tricky if we didn't have that hint. So, like I said, this is something you might see in WebAssign, so I want to prepare you for everything that you might see. The last one, you just have the 1 on the top and you've got a quadratic on the bottom. So you see that, we're going to complete the square. Now it's hard to complete a square when you have 3 as your leading term. So let's do this. Let's make this 1/3, because everything on the bottom factors will is divisible by 3. So x squared minus 2x plus 4 dx. All right, so that makes it a little bit easier to work with. Okay, so now we'll complete the square. So you got x squared minus 2x plus 4. Remember, you want to isolate the first 2 terms. Close the parentheses and put the plus 4 on the outside. Again, we'll use b over a, square it. I'm sorry, b over 2, square it. So negative 2 over 2 is negative 1. Negative 1 squared is plus 1. So plus 1 on the end. And in order to get the plus 1 and the minus 2 in the middle, this would have to be x minus 1 squared. All right, so we added 1 on the right-hand side. You also have to subtract 1 on the right-hand side. All right, so this is plus 3. Well, that doesn't look like a square, but we can write it as x minus 1 squared plus root 3 squared. So anytime you have something weird like that that doesn't have its own square, you can write it like that. Okay, so now when we write the integral, it'll be 1 over x minus 1 squared plus root 3 squared dx. We're still in terms of x here, but we'll change that. So we can let u be x minus 1. du is dx. So nothing to worry about there. No extra multipliers or constants. And then a will be root 3. Okay. All right, so we got 1/3 integral of 1 over u squared plus a squared du. And that's the exact pattern for arctan. So this is going to be 1/3 times, I'll write it out in this form first. Arctangent of u over a, and then plus c. So 1/3 times 1 over root 3 arctan x minus 1 over root 3 plus c. And you just multiply through by that 3. If you want to rationalize your denominators, knock yourselves out. I'm really not concerned about you leaving it like that. So you can leave it exactly like that. All right, so we saw some different techniques there to deal with your inverse trig functions. So again, it's all about recognizing the patterns, right? If you can get something where you see one of these patterns You might have to manipulate it by completing the square or doing something like that. So be aware of that, and always be on the lookout. Is the numerator the derivative of the denominator? Is the denominator the derivative of the numerator? Things like that. So those can all help you out. So be aware of that. Let me know if you have any questions, and have a good weekend.